Good morning, dear students. Today we will study about the inorganic chemistry, the topic number first, which is acid bases, hard acids and the soft bases. See now the definitions of acids are different and the bases are the different. The scientists which they suggested about themselves, that is the one of the Arrhenius scientist who has told about the acids from hydronium ion in water and bases form hydroxide ions in water, whereas at that time he assumes that the water acts as a solvent. Next to him, the Bronsted and Lowry followed the Arrhenius concept and they expanded upon the Arrhenius definitions, which they define acids as a proton donors and the bases are proton acceptors. They also introduced the concept of conjugate acid-base pairs. The other solvents where they explain for any solvent that can dissociate into a cation which has the positive ion and an anion which has the negative ion. The cation is the acid and the anion which acts as a base. Any solute that causes an increase in the concentration of the cation is an acid, and those that increase the concentration of anion are the bases. Let us see about the Lewis acids and the bases. Lewis is also the scientist which he defined the further the expandation of the acids and bases. He told that a base is an electron pair donor and an acid is an electron pair acceptor, and when they two combine there is the formation of an adduct. See the example which is given here. This definition includes the standard Bronsted-Lowry acid-base reaction where H plus aqueous and which reacts with the ammonia in aqueous medium. There is the formation of NH4 plus aqueous. It also includes the reactions of metal ions or atoms with ligands to form coordination compounds. See the examples: silver ion in aqueous medium, when it reacts with the two molecules of the ammonia in aqueous medium, there is the formation of silver nitrate in aqueous medium. Lewis acids and the bases, in this the addition electron deficient compounds such as trivalent boron is categorized as a Lewis acid. In this case, the trimethyl boron when reacts with ammonia, there is the formation of the CH3 thrice boron and there is the removal of that ammonia where it is to be. The HOMO on the Lewis base interacts with the electron pair in the LUMO of the Lewis acid. The molecular orbitals of the adduct are lower in energy. This example which shows that the frontier orbitals, if there is a net lowering of an energy, the adduct is the stable. See the example, BF3 plus ammonia, there is the formation of an acid with LUMO and the HOMO of the base and the adduct which is shown in between. There is the possibility of competing reaction pathways depending upon which reacts are present and the relative energies of the possible products. As a result, a compound such as water may serve as an acid and a base an oxidizing agent with group first A and the second A, those are alkali and alkaline earth metals, or a reducing agent with fluorine. A Lewis base has an electron pair in its highest occupied molecular orbital of suitable symmetry to interact with the lowest molecular orbital of the Lewis acid. The closer the two orbitals are in energy, the stronger the bond in the adduct. The polarization of an acid or base plays a role in its reactivity. Hard acids and bases are small, compact and non-polarizable. Again I am repeating it, whereas the word which explains with the hard acids and bases, those are small in size, they are compact in nature and non-polarizable. Whereas the soft acids and bases are larger in size with a more diffuse and the distribution of electron. In this case, hard and the soft acids and bases, in addition to their intrinsic strength, hard acids react preferentially with the hard bases and soft acids react preferentially with the soft bases. So again, hard and hard interaction is possible, whereas soft and soft interaction it is possible. But more about hard and soft interaction, it is difficult. Somehow, in some cases, it is possible. So it is the abnormal cases in the reaction. The aqueous solubility silver halides, which is given in the table. Silver fluoride it is 205, silver chloride it is 1.8 into 10 raised to minus 10, silver bromide it is 5.2 into 10 raised to minus 13, silver iodide it is 8.3 into 10 raised to minus 17. So silver halides in solid state, when reacts with the water in liquid media, there is the formation of silver ion and the halides they liberate out. Solubility of lithium halides. Lithium bromide, which is higher in solubility than the lithium chloride, than the lithium iodide, than the lithium fluoride. So the lithium fluoride should have a higher solvent than the other salts, yet it is the least soluble in water. This is due to the strong hard acids lithium plus and hard base, which is a F minus interaction. So hard and the hard, there is the formation of the reaction, and soft and the soft, they react with each other very easily. In thiocyanate, the ligand, which is of unidentate, again somehow in some cases in chelate formation it acts as a bidentate also. It displays linkage isomerism as the ligand coordinates to the metal via the sulfur or the nitrogen. Mercury 2 ion bonds to the sulfur, a soft-soft interaction is possible, whereas zinc ion bonds to the nitrogen atom. See the example K of the ligand exchange reaction, that is the strength. The compare MEHgH2O plus HCl, there is the formation of a MEHgCl plus H3O minus, which liberates. And another example, when it reacts with the hydrogen fluoride, there is the formation of again the same reaction, but the constant which is to be increasing. These are the some examples which are showing the equilibrium constant of the reaction of mercury complexes. Hard and soft acids bases, there have been many attempts to categorize various metal ions and anions to predict reactivity, solubility, etc. So the scientists in 1963, R.G. Pearson, categorized somehow the some acids and the bases as either hard or soft using Kf values. Hard acid bond in the order F minus, which is increasing, Cl minus, than the bromine, than the iodine, and the soft acids in the order iodine minus, than the bromine, than the chlorine, than the fluorine. Hard acids or bases are compact with the electrons held fairly tightly by the nucleus. They are not very polarizable. F minus is a hard base and metal ions such as lithium is a hard acid. That's what the strong bond which is formed between the hard acids and the hard bases, and it is formation of a strong ionic bond. Large, highly polarizable ions are categorized as a soft. Iodide is a soft base, and transition metals with low charge density such as silver plus are considered to be soft. So there is the bond which is to be formed with the Pearson concept, that is soft acids tend to bind with the soft bases, and the bond which is formed it is a strong. Hard acids tend to bind to hard bases, soft acids tend to bind with the soft bases. Now see and think about that. The predict the solubility high or low of silver fluoride, silver iodide, lithium fluoride, lithium iodide using hard, soft acid or base approach, and identify each Lewis acid and Lewis base and categorize each as a hard or soft Anyhow, when we are to be doing the reaction in the laboratory or for research purposes, first of all, we have to take care of where that the reaction it is followed with the hard or soft. Then we can go very easily. Charge density of hard acids. Hard acids typically have a high charge density. They are often metal ions with a higher positive charge and small ionic size. The d orbitals are often unavailable to engage in a pi bonding. About the soft acid charge density, soft acids typically have lower charge density, lower ionic charge and greater ionic size, exactly opposite with the hard. Their d orbitals are available for pi bonding. Soft acids are often second and third row transition metals with a +1 or +2 charge and filled or nearly filled d orbitals. It means that the incomplete d orbital or filled d orbital. Let us see on the borderline, see that categorization of the acids. Hard acids which are shown in the table, borderline acids, these are also shown, and the soft acids. So hard acids tend to bind with hard bases, soft acids tend to bind with soft bases, but the borderline acids and the borderline bases, sometimes they react with the harder or react with the softer bases. Effect of oxidation, which is shown in the table in this case. The basis, which is also shown in this table, and the reaction and the molecules which are to be bonding with each other, that is mentioned. Basis effect of oxidation, that will also explain here. Effect of linkage size. This thiocyanate, when it is bonded with the nitrogen atom or when it is bonded with the sulfur atom, see how it reacts. The nitrogen tends to coordinate with the harder acids such as silicon, whereas the sulfur tends to coordinate with the softer acids such as platinum. So when the nitrogen bonding it happens with the thiocyanate, it is hard, and when it is bonded with the sulfur atom, then we can easily suggest that it is a soft side. Effect of oxidation number. Copper 2 plus to copper 1 and acid hardness. SO3 to SO2 on acid hardness. NO3 minus to NO2 minus on base hardness, and SO42 minus to SO32 minus on base hardness. This trend, it is important to realize that hard or soft consideration have nothing to do with acid or base strength. An acid or base may be hard or soft and also be either weak or strong. In a competition reaction between two bases for the same acid, you must consider both the relative strength of the bases and the hard-soft nature of each base and the acid. See the example, the reaction between zinc oxide and LiC4H9. In this case, zinc oxide when reacts with the two molecule of LiC4H9, there is the formation of zinc C4H9 twice plus Li2O. Zinc ion is a strong Lewis acid and oxide ion is a strong Lewis base. And that's what there is the formation of the strong bond and there is the release of that Li2O. Consider another reaction with the zinc oxide and LiC4H9. In zinc oxide, zinc is the strong, soft and oxygen is the hard. And LiC4H9, Li is the hard where C4H9 is the soft. And according to the Pearson concept, the reaction must be followed with the soft and the hard. And thus the reaction which proven that zinc C4H9, the bond which is formed with the soft and the soft nature hard and base, and Li2O, that is hard interaction which happens. Zinc ion is a strong Lewis acid and oxide ion is a strong Lewis base. However, the reaction proceeds to the right, that is K is greater than 1, because hard-soft consideration override acid-base strength considerations. The nature of the adduct. Hard acid, hard base adducts tend to have more ionic character in their bonding. These are generally more favored energetically. Soft acid, soft base adducts are more covalent in nature. So hard interaction, it forms with the ionic bond, and soft interaction, which forms with the covalent nature. Other considerations, as the adduct forms, there is usually a change in geometry around the Lewis acid. BX3 plus NCH3 thrice, there is the formation of X3B and NMe3. The stability of the adduct is BBr3, which is greater than BCl3, which is greater than BF3. This order seems opposite of what would be expected based on hydrogen size and electronegativity. The other consideration which shown in the diagram, the reactivity pattern suggests some degree of pi bonding in BF3. Empty 2p orbital which is shown and the filled orbitals, they are in the bottom. Steric factors can play a role with the formation of hard-hard and the soft interaction. The example is the unfavorable reaction between N66H5 thrice and BCl3. The large phenyl group interact with the chloride atom on boron to destabilize the product. Let us see about the applications. The Quell scheme, a series of chemical reactions used to separate and identify the presence of dozens of metal ions, is based largely on the hard and soft properties of the metal ions. The softer metals are precipitated out as chlorides or sulfides, with the harder ions formed as carbonates. In this slide, which is shown that hard, soft, acid-base acids, soft acids, borderline soft acids, borderline soft, hard and the hard, which is shown in the group 1, group 2, group 3, group 4 and the group 5. The reagent which are explained and the solubility which is given. The precipitates which is formed, that is also given on a slide. In geochemistry, the elements in the earth crust are classified as lithophiles or chalcophiles. The lithophile elements are typically found as silicates bonded via the oxygen atom. Lithium plus, magnesium 2 plus, titanium 3 plus, aluminum 3 plus and chromium 2 plus 3 plus. These are hard Lewis acids. Whereas in chalcophile, elements are typically found as sulfides or bounded to selenium 2 minus, Te2 minus. They include cadmium 2 plus, lead 2 plus, Sb3 plus, bismuth 3 plus. These are soft Lewis acid. Zinc ion, which is borderline, is typically found as a sulfide. So, the students, I think you have understood clearly the nature of hard and the soft acid base, which is explained by the R.G. Pearson in 1963. Be safe, take care, wash your hands frequently, use mask, take sufficient Indian food and maintain your social distance. Thank you very much.